Hi, my name is Oliver Stevens, and this is the first video in a series of CPA webinar type things. Yeah, so not sure how many there'll be, but today we are going to do the first one. So yeah, I'm Oliver Stevens, and I'm a mastery specialist leader with education, and PD lead trained with the Maths Hub, Yorkshire Readings Maths Hub. And in part one today, we're going to look at addition. So to have a clear understanding of what CPA is and how it supports pupils' understanding and progress, to be able to use the part-whole structures and bar model with addition for Key Stage 1. Okay, so the way you might use this is you might use this video in a staff meeting, so you can run some training using this video by pausing it and going through the training, or you might be using it for individual CPD or small groups of teachers. However you want to use it. I highly recommend doing the pausing and activities because that means you're going to get more out of the training. And I would also recommend you have a whiteboard or some A4 paper, possibly even some counters out. You could have some one-to-one counters, correspondence. You won't need any base 10 for this first session, but as we get deeper into it, you might need some place value counters and base 10. Wouldn't hurt. Okay, lovely. Here we go then. So, key terms, what is CRA or CPA? So we're looking at the concrete, pictorial, abstract methodology today. So this is kind of a linear model, but this is also cyclical, okay? So let's define our key terms. So concrete is practical structural operators, including cubes, counters, shapes, weights, coins, and objects, anything you can get your hands on, okay? Representational includes drawings, diagrams, and images, including number lines, calibrations, bar models, 100 squares, yeah, pictures of base 10, drawings of base 10, anything like that, drawings of place value counters, okay? And then the symbolic from this diagram here, but also interchangeable with abstract, is the numbers, number sentences written in expanded methods, and also anything you're saying as well, if you're reading a number sentence and saying it out loud. My top tip here is keep going back to the pictorial and the concrete, okay? Don't just do concrete representational abstract. We've got to the abstract and we're never going back to it. We've got to the abstract, say within addition, for example, we're going to keep dipping back into, particularly for me, the pictorial. I'm going to keep going back and making sure that they can draw a picture and explain to me the mathematics behind it. And this is so important. Okay, so keep going backwards as well. And why is visual maths, why is this CPA model so important? What is so important about visual mathematics? So this is taken from Joe Bowler. Visual mathematics is an important part of mathematics for its own sake, and new brain research tells us that visual maths even helps students learn numerical maths. In a groundbreaking study in 2013 found that most powerful learning occurs when we use different areas of the brain. When students work with symbols such as numbers, they are using a different area of the brain than when they work with visual and spatial information, such as an array of dots. Research found that mathematics, apologies, I'm not editing that out. Mathematics learning and performance was optimized when the two areas of the brain were communicating. For maths questions that encourage the use of visual and symbolic representations, go to UCubed, which is a great website. Additionally, they found that training students through visual representations improves students' maths performance significantly, even on numerical maths, and that the visual training helps students more than numerical training. That's why it is so important. And in her book, Joe Bowler, I think it's called Mathematical Mindsets, Joe Bowler goes on to elaborate that when you are doing maths, there's a potential 60% of the information can be visual, so visual spatial, yeah? So number lines or bar models or part-whole models. 60% of the brain activity that's possible during a maths activity is dedicated, 60% of that is dedicated to visual spatial information. So if your teaching does not include currently a representation for the majority of the problems that you are looking at, or at least at the beginning of a lesson sequence, you're missing out potentially on 60% uptake of each student's brain power. For me, that makes it really powerful and thoroughly worthwhile. So please do bear that in mind, that's 60% in mind as we go through this. Okay, so in terms of teaching for mastery's big five, we are obviously looking at representation and structure. Okay, let's say this together. 5 is a part, 3 is a part, 8 is the whole. Okay, so part, whole. Okay, or if you've got unifix cubes in your hand, say, 5 in this hand, 3 in this hand, and then 8 is the whole. So 5 is a part, say it with me, 5 is a part, 3 is a part, 8 is the whole, okay? 5 is a part, 3 is a part, 8 is the whole. We've got our part, whole. So a good bit of chanting to be done with our classes there. Let's move on. So let's have a look at this problem. These resources were taken from the NCETM Spines, year 1. So there were 4 open umbrellas and 5 closed umbrellas. We can write this as 4 plus 5. The 4 represents the open umbrellas, we can see here. The 5 represents the closed umbrellas. And here we can get children to make a model of this themselves, perhaps with 2 different colored counters. So I was shown this before. So if I was teaching this as part of a lesson sequence, focusing on my representation, my CPA, I would ask the children, or I would model with the children, right? Everybody, let's get our part whole models out. Let's have our counters here. What do the red counters represent here? Yeah, so the red counters represent my closed umbrellas. 1, 2, 3, 4, 5. 5 red counters there. And actually, I'm looking at this now, and I probably should have switched my part whole model. So I'm going to do that now, because I want my 5 on the same side, just to build that bit of connection. So I'm going to swap that over to maximize the connection. You might also notice the way that I'm arranging them slightly differently, but I'm going to stick with that one. Okay, let's go again then. Okay, so I'm working with my class, I'm modeling that I'm making my part whole model. I'm going to say to my children, right, what do my yellow counters represent? What does 1 yellow counter represent? 1 yellow counter represents 1 open umbrella. Okay, so I'm going to say that, and we're going to say that 1 yellow counter represents 1 open umbrella. And how many open umbrellas are there? There's 1, 2, touching them if we need to, 3, 4, touching the counters if we've got them in front of us, yeah? Okay, someone else in the class, what do my red counters represent? My red counters represent, 1 red counter represents 1 closed umbrella. And that is a 1-to-1 correspondence. 1 counter here represents 1 thing, 1 real thing, 1 closed umbrella. So let's go over that again. 1 counter represents 1 closed umbrella. Excellent, fantastic. And we have 1, 2, 3, 4, 5. Fantastic. So we know 4 is a part and we know 5 is a part, and we need to find the whole. So 4 is a part and 5 is a part. What is the whole? So we need to put them into the whole. So I'm going to move my 4 up. I'm going to move my 5 up. So 4 was a part and 5 was a part. Make sure we get them all in the hole there. We're going to do 4, 5, 6, 7, 8, 9 is the whole. Fantastic. We say 4 plus 5 makes 9. Let's say it together. 4 plus 5 makes 9. 4 was a part, 5 was a part, and 9 is the whole. Yeah, fantastic. And if you've been really switched on watching this, you'll notice my sentence stem is back to front, but never mind. All edits are free of charge. All mistakes, sorry, are free of charge, the irony. Yeah, so we've got that there. So really important that we're going over that sequence. Okay, right. The part whole model here is a model of the problem. So this is a really important part for us to draw out as teachers to reflect on ourselves. The part whole model here is a model of the problem. Okay, Mike Askew in his book Transforming Primary Mathematics talks about this. Creating a model of the problem. So this is a model of the problem because there were this 5 umbrellas and there were 4 umbrellas. I've gone back to having them the wrong way around. Yeah. Fix that. There we go. Yeah, there were 4 umbrellas and there were 5 umbrellas, 4 open and 5 closed. So the model of the problem is we needed to find out how many there were in total altogether. That's what we didn't know. That's a model of the problem. That's what's happening within the problem. And then you might have a separate model for calculating. Now, in this case, we used the same model for calculating. We counted up. Yeah, we moved them all into the whole circle, and then we counted up. That's fine. Later, as we go deeper into this journey, we might find that in some cases, we want a separate model for calculating. So I just want to make that distinction now. The model of the problem, which is really important at every stage of learning, the model of the problem and the model then for calculating. These two things that Mike Askew has drawn out in his book, Transforming Primary Mathematics. Okay, so here, if we wanted a separate model for calculating, we might have said, actually, we're going to start on 5 because I know that's the larger number, and I'm going to count on 4. 1, 2, 3, 4. There are 9 umbrellas altogether. Okay, so that would have been using my number track here. That would have been using my number track here for calculating. That isn't a model of the problem as such, although we could argue it is. But I'm trying to make a distinction here between this being a one-to-one correspondence because these equal 1. Yeah. Whereas it's harder to see in this representation. It's harder to see where the umbrellas are. Yeah. That's very, very difficult because each umbrella is not represented within that number line. It's a more abstract, if you think of it on a continuum, it's a more abstract representation. Okay. Lovely. So I'd like you to have a go now. I'd like you to pause the video, read the word problem, and have a go. So there were 6 boys lining up for a class race. Then 3 girls came and lined up for the race. How many children are lined up for the race now altogether? I highly encourage you to pause the video and make a model of the problem and discuss with the partner which part represents which part of the number story of the word problem. Discuss with your partner what model the children might use for solving the problem, and discuss what sentence stems you would use with your class and maybe have a practice of that. And this is really, really valuable practice for you and discussion with your partner or your team if you're in a team. So pause the video now and then come back to me. Lovely. Right. I hope you had a good, that you had a go at that and got some valuable discussion out of it. So let's have a look at this. There were 6, so same problem, I'm just going to unpick it a little bit. There were 6 boys lining up for a class, then 3 girls came and lined up for the race, for a class race. Then 3 girls came and lined up for the race. How many children are lined up for the race now? 6 plus 3 is equal to 9. 1, 2, 3, 4, 5, 6. 1, 2, 3. Yeah. So we've got our representation. And it's really important. Please don't discount. Please make space in your math lessons for informal representations. So this is a very informal representation of the start line of that race. Okay. And it's really important that children have the opportunity, I would argue, that they have the opportunity to represent that. And what that is making a model of the problem is it's the comprehension level of that problem. So it's getting the comprehension out. What is happening, yeah, in that problem? So first these boys were lined up, and then these girls came along. Now they are all lined up, and it's the comprehension level of that problem. Okay. And again, we'd question, what does one red counter represent? One red counter represents 1 boy lined up ready for the race. What does one yellow counter represent? One yellow counter represents 1 girl lined up for the race. So we're checking that we have the comprehension of the part-whole model as well. Yeah, and hopefully if we're saying that together, a little choral saying, so we can say all together, 1 red counter represents 1 boy lined up for the race. We can all say that together, that no one in the class is escaping. Yeah, the understanding. Everybody's saying it and engaging with this model in some way. That's good practice when it comes to teaching for mastery. Okay, 6 is apart. So then we can say, well, we needed to put them all together. And I had carefully chosen my representation and then I went and disturbed it. Okay, we can put them all together. I think actually, there's another interesting choice about how we arrange them within the part-whole model. 6. So we know we had 6, 7, 8, 9. Fantastic. 6 is apart, so maybe holding them. 6 is apart, 3 is apart, and 9 is the whole. Let's say it together. 6 is apart, 3 is apart, 9 is the whole. 6 plus 3 makes 9. Let's say it together and get everyone involved. So hopefully from that question and from that little bit of a reflection, you've got something out of that. Yeah. So those were 2 models of the problem, and we may have used, if we wanted to, a number line or number track for calculating. Okay, let's move on. So I wanted to draw out another teaching point from the same question. Another important part of the journey is from the concrete to the pictorial. So top tip, remove the counters directly and replace them one at a time with representations. This is key to pupils' understanding of the representation, and some children do not make this link. So something you can do is remove a counter we can draw even more powerfully, we can draw around the counters before we remove them. So that drawing becomes, that now represents one counter. And that representation of a counter represents one boy lining up. And you can see, as adults, we would very quickly make that link. But there are some children, and I was probably one of these at primary school, there are some children who are going to miss that stage and need us to explicitly model and walk them through that. So I would implore you to consider incorporating that into your teaching sequence. Okay, and you can do it with the other counter, and you can do it with all of them. Okay, so that eventually those counters become replaced with, oh no, I haven't got it down there. The representations of the counters. And that's an important part of the teaching and learning sequence. Once we've explored this stage where we are drawing counters, we can then consider moving into the abstract. And you can see here very clearly, I mean, I know I've got pictorial counters, but if we had physical counters in the classroom, I would highly encourage getting counters and sticking them onto the wall on a part-part whole model so that you also have something that's concrete to make that really explicit. Okay, so you have moved them from these real counters, even though mine are visual and technological, yeah, from real counters that the children have in part-part whole models to pictorial counters that they're drawing onto a part-part whole model, and then replacing that with 6. And this is why that symbolic comes in. That squiggle is a representation that stands for 6 counters. You can't see the 6 counters, but what we must do is attach as much meaning as possible to that squiggle 6, that symbol 6. Okay, that's really, really important. And then we end up here. Okay. So this is key to pupils' understanding of the representation, and some children do not make this link very easily at all. And you know, I can attest to a lot of lost progress here, a lot of lost learning time. Okay, so I highly encourage you to make use of that. Right, moving on to some year 2 materials now from the NCETM spines. Okay, so we can see we have 2 red counters, 3 blue counters, and 5 yellow counters. How many counters are there in total? So my concrete here would be I could get a tens frame, and if I've got access to 3 different color counters or 3 different color Unifix cubes, I can put my Unifix cubes or my counters into my tens frame. Okay, notice here how I've chosen to structure it as well. If I'm modeling to the children, I chose to make 5 first and then fill up the other 5. And then it's very, very structured and purposefully thought through. Okay. So that's my concrete if I've done that with physical counters in the room with the class. My representation here, these are representations, but I also have the pictorial, so the pictorial stage. This is pictorial, but this is also, so this is abstract, but it's also pictorial within the abstract. So the abstract part being that I have the numerals represented here, but I also have a representation of the problem. So first this, so make it physically first, then represent the problem, because we knew 2 was a part, 3 was a part, 5 was a part. What was the whole? 10 was the whole. So let's say that together. I'm going to say it again. Say it with me. 2 is a part, 3 is a part, 5 is a part, and 10 is the whole. Okay. So we're going through, this is a very, very similar sequence. Yeah. We have the concrete, hopefully if we get our counters out, or our unifix cubes, we have a representational stage mixed with an abstract stage here, so blending those two together. And then we might be that we need to move to this, to our number track here, our number line, sorry, our number line here, in order to calculate. Okay, so that might be that this is then my model for calculating. So this would be my model of the problem. This would also be a model of the problem, a different model of the problem, but an equally valid model of the problem. And this will be my model for calculating, that I would do 2, add 3, 1, 2, 3, add 5, 1, 2, 3, 4, 5. I know that there were 10 marbles in total. We say 2 is a part, 3 is a part, 5 is a part, and 10 is the whole, keeping that nice and consistent. Okay, time for you to pause the video and discuss with a partner how a child might transfer their part-whole skills to this problem. Please draw a representation of the problem that might scaffold the learning for a pupil. Okay, so pause the video, have a go, and talk about the sentence stems as well. Off you go. Okay, I'm going to assume that you've come back to me. Let's have a look. How did you get on? First, model of the problem. So this is my pictorial stage, also blended with an abstract stage. So I knew 13 was the whole. Okay, I knew 13 was the whole. And possible support, children could draw 13 counters or dots and partition them in different ways, trial and error, in an attempt to match to the above number. Okay, so I had to think, this is also a representation of the problem. I knew that I had to split it into 3 equal parts. And so I drew myself 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 counters that I knew I needed to partition into 3 parts. They didn't have to be equal. That was an important part of the structure of the problem. Okay. And then I knew I needed to match my 3 parts to numerals represented here. So a child could start with a bit of trial and error. I started with my 2, my 6, and a 5. But I can't switch my brain. I'll find out. I know some bonds to 13. Okay, 5 is a part, 6 is a part, and 2 is a part. 13 is the whole. I said that a little bit wrong. 5 is a part, 6 is a part, 2 is a part, and 13 is the whole. Okay, so hopefully you can see the transference of skills here. They need to know part-wholes, but also the importance, or I think the value of an in-between stage of an informal representation. Yeah, so giving children the opportunity and validating informal representations, I would say, is incredibly valuable, and in my experience is. Okay, so just to recap that's the end of episode 1, or video number 1 in this series, however many there end up being. So just to recap, make models of problems, use concrete materials within part-whole structures, consider your use of sentence stems to reinforce the key learning, consider the fragile steps of moving from concrete to pictorial to the abstract and how you can add meaning to each step. Remember to check that children understand what each part of the calculation represents. Okay, right. I hope you got something out of that as a team or individually. I'm going to be uploading these onto YouTube. Please do drop me comments onto the YouTube channel if you've used this in a staff meeting, where you are, and the impact that it's had on your school. Press subscribe to the channel, and watch out for the next videos in this series. So hope you've enjoyed. Take care. Bye for now.